Uh, Hi, today I'm going to talk about my project, Quantum Chromodynamic, and I will explain it from following aspects, begin with the most basic facts, then develop its application, and if it's possible, I will teach them equations and properties. Okay, here comes the very first part, which is the introduction of quantum. I believe that most of you have heard one news or even more of it. At least I've heard news reported from my parents' room many times. As usual, people will consider it as a concept that only belongs to scientists, which normally people will not never touch. Actually, quantum is quite intimate, especially we know them hidden in every place on the planet, as to around us. We can find them inside an atom, from the laser beam we saw in the show, the functioning power station, also in a nuclear fission like the ignition of a nuclear weapon, in a red or blue giant star. From the phenomenon of celestial we discover through telescopes to the microscopic world under highest technology. Quantum is basically everywhere. Like Asian says, ensemble la beauté est partout, n'est point qui manque dessus, mais nous qui manque la percevoir, which basically means beauty is everywhere. It's not she who is missing in our eyes, but our eyes that fails to see it. Hopefully, I have delivered my ideas to you since I don't know French neither. Back to our PPT. All images above can be analyzed into four groups. The electromagnetic interaction, weak interaction, gravity, and strong interaction. There are four elementary forces that sustained our universe. From left to right also can be grouped into two, the long-term force and short-term force. However, due to my topic is QCD, so I'm only going to talk about the strong interaction known as the strong force. Additionally, I promise to everyone that I will not show anything like this, and I can assure you that I'll finish this as easy and simple as I can. Alright, so what is strong? What is the strong force? In short, it's a force that bonding protons and neutrons together in a nucleus and avoiding electromagnetic forces repulsion, ripping off the atom structure. Clearly, strong force took an important job at maintaining particles and supporting our microphysics principles. That made it become a respectable member of four forces. Science shows that we use the concept of color to represent the strong force property. Likewise, in QED, we have electric charge to show the property of protons and electrons' interactive behaviors. Meanwhile, we found that QCD is a bit more chaotic, so three colors are advocated to explain those quantum behaviors. To have a better ideas of understanding, each quantum dynamic series proposed at least one kind of chart. In QCD, the color chart was being mail delivered. Those mails contain information of everything that a quark needs to forming a field, just like we did. Receiving mails through fibers, so does they do. Gluon takes the role of mail messenger carrying the mail of quantum information to forming up a force field. And as soon as quark receives those information, it leads this tiny system to interact with other system. The faster gluon delivered, the more energy that this system transferred, the stronger field produced. In standard model theory, the formula indicates that bosons, the force carrier, and fermion combine together and forming up every particles we have discovered. Obviously, we can't finish learning each of them that's shown on the PowerPoint. However, there are two that I want to emphasize. The first one I want to mention is gluon. Gluon is not a glue, so do not mix the content with that. Nevertheless, we can imagine that gluon is a glue that glue strong interactive particles together. Because we have no ideas how gluon really exists and works. So in this way, it's easier for beginners to understand. And here's some information about gluon, the boson of strong interaction. The left side is the equation to determine the color combination of gluon, and right side is the formula to describing quantum systems dynamic status. The reason that here stated regarding gluon may not blast as you thought is due to its being a boson. Lots of properties didn't exist on bosons. Otherwise, gluon will be like other fermions are soon to talk about. After we finish taking a look at the slide, we are moving on towards the big camp of the following particles. This is the big one in whole presentation. Quarks. Quark is the fermion who bring out itself directly towards the savior of strong force. Due to the property of any boson, gluon can have any interaction with other particles, neither electrons nor W or Z bosons. Hence, quark in this case then the placement of connecting gluon and the force outside. Therefore, quark itself is really dependable in QCD. Quark being the biggest group among this theory system has 6 classes and 36 types, which made QCD become one of the most difficult study in physics ever. After decades of studying quantum, we found that most quarks listed above are very diverging. From the lightest of only 1.7 mega electric voltage per c square to like 1.7 no, it's like 172,000, which is basically 172 giga electric voltage per c square. That's heavier than an atom of tungsten. Quark is so strange in its behavior, and one extreme example is the string quark. Like its name, the oddest things that happens on it disobeys the principle of color confinement. This quantum can stand alone and bounce with other quarks without limits. If this prediction is correct, then I can tell there's a quantum in the space somewhere has already started cannibalism of quark viruses. Causing string quark can be a homogeneity. Under such energy level, any matter can be assimilated by force. In that case, fermion in standard model will be imbalanced. Consequently, the world will be left with extremely low temperature and deadly barren. Although this might be terrifying, in virtue of the Big Bang theory, the expansion rate of quark disease will never approach our galaxy. What a fortune that is not our business. We need to worry about it yet. Besides that, even weirder things happens is that quark has not only just the electric charge and color charge, but also has another property called flavor. Flavor is a concept in QFD, or as we call the weak interaction. This means that quark basically attending each force we have discovered. Study shows that weak interaction is one of the rarest forces in quantum theory. Regarding weak interaction, there are a few things we need to know. That it has the shortest interactive range ever. It's about 1,000 times shorter than Q's gluon, and this made it become very unlikely to occur in any condition. To start a weak interaction, we can only see it during nuclear fission and subatomic radioactive decays. Only in that environment, weak interactions can overcome strong force between quarks and by time for electromagnetic force to repel thin electric charged particles, which lead to nuclear decay. Being honest, I don't know if you have found this concept took the longest time for me to talk about. The reason is that the study of quark has made QCD become so complex, and great percentage was caused by its flavor and color dynamics properties, especially weak interaction. Uh, as we know, it's the only one theory that we discovered that quantum and antiparticles have different weights and properties. In other words, when you look in the mirror and you found out a person you had never seen before doing the things that you didn't do at the moment. That's what weak interactions did, and thanks to the contribution of Chen Yang, a CP violation which interprets the odd behavior in weak interactions. Scientists finally solved this problem in last century 50s. Due to that discovery, he became the first Chinese physicist who won Nobel Prize. That's really great work though. After all, we left only one part, which is it possible to apply those particles and theory into our daily life? Well, since we have uh, learned some basic knowledge about QCD, we should tell that if we succeed in doing that, uh, then we might need to have break into a completely new era. So before we talk about this, about its benefits, we should figure out whether it's worth or not. Nowadays, scientists had already found a way to separate gluon from other particles, and that accelerates a particle beam and aim it for a collide. We call these gigantic machines colliders, and they're really big machines. And as I know, they're the biggest machine we have ever built. Like Hog in an industrial machine, and countries come around and work together to build about a dozen of these instruments. Each of them were designed to work with different environment for different purpose. So LHC, Large Hadron Collider, is one machine specialized to find high-energy particles, fragments after light-speed particles collision. 5 detectors were placed to help scientists record data within billions of 1 seconds. That's less than 1 nanosecond. To reach that, the condition for hadron became free to escape interactive field. We need land to build machine as big as this one on the screen. Indeed, yes, it's shocking. Our school looks so tiny when we compare colliders and former together, and it's on the bottom left side. Uh, and This brought us several questions. How can we manufacture great numbers of strong interactive materials with few bulky and power-swallowing monsters? Since electric can have no control uh, of gluon, then we should take care. How should we take care of those particles? Can any power station afford for power to such machines? Many more. And my answer for those mentioned above is not yet. Our technology in present has not reached a level of applying quantum tech widely, and now scientists can have opportunity to have contact with them. We are still trying to study them, and I believe in the soon future, with the help of new breaking discoveries, we can eventually find a way to chart these minor skies. So that's the end of my presentation, and thanks all for listening and watching.